Lab team for allowing me to be here telling you this story about AI-based real-time decision making. So let me jump right into it. So I'm co-founder of AQI. AQI is a company that is helping enterprises adopt AI by developing custom AI solutions. And if you want to know more, we can chat after the presentation. But today I'm gonna go through a case study of actually developing AI applications for a real-time decision-making problem. And this is a case study in motor racing. So how many of you are F1 fans, or have at least watched an F1 race? Okay, that's a pretty good turnout. I think everybody has an idea more or less of what happens in this racing business, right? Motorsports is certainly a very competitive industry. When I came to it to work on this, I wasn't really a fan and I didn't know much, right? But one aspect of it that immediately caught my attention was the fact that, in motor racing, maybe unlike other sports, you have a combination of a pilot, of a human, and a machine, right? So already you are starting with someone working together with a machine to achieve a particular objective. And at the beginning I thought, okay, this is just people, pilots, very skilled pilots, managing these crazy machines, trying to go as fast as possible to win the race. But there is much more behind it in the process. So the pilot is the person responsible for taking the action, right? That pilot is driving the car. But behind the pilot, there is a group of people that are making the decisions about what the pilot should do. Should the pilot go to the pit? Should the pilot accelerate, try to pass another competitor? Should the pilot save fuel in order to make it till the end of the race? All of those decisions are actually made by a group of people, the strategists that are working with the pilot. And if you have watched F1 racing, for example, you have all of these audios of the strategists talking to the pilot, right? And that actually make it's part of the fun in F1. So there is that aspect of the decision making, but there's also the aspect of the car. So cars today have evolved, and we have seen, this morning we saw a lot of examples about autonomous cars and how cars are how people are putting more and more sensors in these cars. And that is definitely the case also in motor racing. So, each of these machines is equipped with not thousands, but hundreds of sensors that are collecting a lot of data. And that data is presented to the strategists to make decisions during the race. So, the amount of data is getting to a point where strategists are getting overwhelmed with all of the data that they have to make the decision. And this makes it the perfect example or the perfect case to apply AI. How can we apply AI models to make that decision-making process easier, to help the strategists make those decisions, process some of that data? So the team at AQI worked on in a previous company, we worked with a race team developing these AI solutions. And what I'm gonna tell you about today is the experience of going through that process in developing those models. So maybe to give you a little bit more details about the use case, right? So, this is the typical layout of a track. Actually, this is an oval, which is something that F1 doesn't have, but that IndyCar does. So, you have the car is going through the track, but the track is equipped with a bunch of points in the track where you are collecting information from the car. And that information is the information displayed, to the strategists. So, they are watching to a bunch of information of what's happening at the race. Who is winning? What is the pace of the cars? What are the lap times, right? And they are making decisions based on that. So how they get that information, you have tens of packages that are being streamed. Every time a car crosses one of those points, some information is collected from the car and then sent via telemetry to these guys. And that happens in the order of milliseconds. So they are getting all of these live information about what's happening. And they need to make critical decisions within a minute, typically, right? Because, a lap might take a minute, and, they might decide, are we pitting or not? They have very short time to make that decision. And they are certainly overloaded by a lot of information. You have video, you have audio, you also have a lot of time series data that is displayed to them. and that was the focus. That time series data was the focus of this study. And those here definitely is a very competitive sport. You have differences in milliseconds can determine a race. So certainly critical decision making. So what are more specifically the decisions that the strategists are making here? So one of them is, when should the car pit, right? When should they replace the tires, refuel the car? What tires should be used? This is particularly important for example, IndyCar racing. Are they picking the tire that is softer and can go faster, but it's going to degrade faster as well? Or are they choosing the harder tire, right? That's a very important decision for the race. And should we save fuel? That's another important decision that they make. So these decisions are made by the strategists. And then the action, right, just to connect to what we saw this morning, we have all this pipeline from data all the way to an action, right? The action is executed by the driver, but the decision is taken by the strategist. And what the strategists are trying to do is to gather more knowledge about what they should do. And that knowledge, for example, how quickly are the tires degrading? Or what is the expected lap times of the cars in the future, a forecasting problem. When will an accident will happen, right? Which will change from green flag to yellow flag and impact the strategy. These are the type of, this is the knowledge that the strategists would like to have to make those decisions. And in this project, we were using AI to provide this knowledge. So the AI was acting at the layer of providing knowledge, not yet making the decision. The decision is taken by the strategist. It's still a human in the loop process. And the information that we were using was essentially information like lap times, speeds and acceleration patterns. This is all information that at the end can be interpreted as time series data. So that's the layout of the problem. And at this point, maybe if you are coming from, there are people here from different industries, you might start thinking about, how this problem might be similar to some problems that you are experiencing in your own industries, right? Maybe if you're coming from manufacturing, you are thinking, oh, we have the sensors in the plant, and we are trying to use that information to determine where we should change something in our planning, or stop the production or restart the production. If you are coming from finance, you are thinking all of this information that the traders have to process in order to make a decision. So as I go through this process, think about how the process here might be analogous to some of the process that you will have to do if you want to implement AI in your industries. So in order to develop AI for helping in this decision-making process, we follow this general process of going through these 4 stages. And you saw an example of that this morning as well. I will go through the stages and tell you essentially what we did, what was the outcome of these stages for this problem. So the first stage is discovery, right? So it's important when we think about implementation of AI that there is always people involved. There is a people aspect of AI that is important to take into consideration. And typically you will have to bring different expertises to get an AI outcome. So at this discovery phase, you will need someone with expertise in AI, but you will also need to talk to the business stakeholders. Who are the people that are going to benefit from the AI, right? What is the KPI? What is the change that you're going to make in your service, in your product, that is going to drive value because of the application of AI? And that's typically information that the stakeholders have. But also, who are the subject matter experts, right? So who are the people that deeply have knowledge about, that have a deep knowledge about that problem? And you will have to go through a process of assessing what data is available for you to use and what are the requirements of that solution. So in the context of the project that we did, we discovered that there was a lot of data available, but a lot of that data requires some annotation, to the point that we described, a point we saw this morning. We also discovered that not all the data was usable, just because through time, the data schema, the structure of that data have been evolving. Season to season, they might replace a sensor, and then that adds a different type of data or remove a data point from one year to another. So there was data available, but we had to first figure out what data was usable. Which insights will have the most value? Then we try to prioritize the use cases, and we'll go a little bit more into the details of that. How accurate and fast should the predictions be? Quickly we realized that this was a problem where we needed to apply this AI in an online mode. Meaning that during the race, the AI model should be doing predictions and displaying those predictions to the strategists, who in this case are the users of the solution. And this needs to happen very quickly, and I'll tell you how quick in a second. And another important point is, what is the next best alternative, right? So in this case, if they are trying to answer a question, how are they answering that question today? Are they using a different model, a different algorithm, or is just human intuition, right? So only by having an understanding of what is let's call it the state of the art for the company today, then you can do an assessment of how much AI is supposed to improve upon that reference. So in the case of this project, we identified 4 use cases. The first use case was pit stop and tire change optimization. So turns out that you can actually formulate the problem of when the car should stop and what tires should be used as an optimization problem. So some people might not consider optimization part of AI, but it's a complementary capability. I would consider it part of it. And that was actually the first problem that we tried to address in this case. The second was anomaly detection. They really wanted to know when an accident will happen. The accident will produce a yellow flag, and when you go into yellow flag mode, your strategy changes. Sometimes yellow flags determines, you should pit to take advantage of the yellow flag. So they wanted to know if it was possible to make predictions of when, or anticipate when the accident was going to happen. And then there were opportunities also for predictive modeling. Specifically, they wanted to be able to predict lap times. So based on the information that we have of lap times, what the lap time is going to be in the next 5 laps. And also they wanted to understand tire degradation. Based on the speed of the cars, as the car goes through the track, the tires degrade very quickly. That's why they need to change them. And at some point, it actually becomes dangerous, because if the tire has degraded a lot, the car can slide and cause an accident. So they want to maximize the use of the tire. So they want to replace the tire just before that is going to happen. And that is very, it's very hard to determine when that is going to happen. So they wanted to have a more quantitative way of doing that. So we went through a process of talking to them, understanding the context of these problems, figuring out if there was data available to try to produce them, to produce a model, and that took the first part of the project, actually, just understanding what the use cases are, what were the problems that they were trying to solve. And then after that, we jump into a prototyping phase. And at this phase, you need to involve data engineers, machine learning solutions, software engineers that can build these models, and you continue that interaction with the subject matter experts and the stakeholders. But the first piece of this is the data infrastructure, right? Like what data is available, how we connect the data. So in the case of this problem, as I mentioned before, one important point is that this is an online machine learning problem. What that means is that you are going to have a prompt. At some point, you're going to receive some information, and you are going to use that information to make a prediction. And you are going to receive these packages of information every certain amount of time. In this case, we're talking actually several packages per second. So we needed a platform that this diagram essentially is just an abstraction of the ML infrastructure that we built for this problem. So an important piece of this is a piece that can manage event streaming, right? That can actually deal with data in a streaming format. And in addition to that, we needed, of course, a data store, a place to put the data, both the historic data as well as the data that we are collecting. We need a computer orchestration tool, and I'll talk more about this, but an important piece of this AI solution is, where are you doing the computation? Is the computation done in the cloud? Is the computation done on-prem? How close the computation needs to be to the place where the decision is taken. All of those are considerations in the design of the solution. And of course, model management tools that enable to, for example, to keep track of your models and catalog them. And on top of that, you might also need custom applications, right? So the model makes a prediction. How is that prediction displayed to the final user, right? Is it a dashboard with some type of dial? Is it a plot, right? How you're going to display that to your user actually is very important, because depending on that, the user might want to use it or not, right? And at the end, if you build a model, you want people to use it. So that has to do with data. Now let's go to the other part of prototyping. Now we figure out an infrastructure to build the models and get the data. Now we need to figure out which models are we going to use. So I told you about these three problems that we wanted to solve: tire degradation, lap time prediction, and yellow flag prediction. And I think an important point that we learned from this experience is that different problems have different modeling needs. And today people, of course, are very excited about ChatGPT and what ChatGPT can do, but ChatGPT is just one specific type of model. And it has some specific set of use cases. It will not be able to serve every model, every problem. Furthermore, it might be the case that the solution to your problem is something way simpler. You might not need something extremely sophisticated to still provide value. So in the case of these use cases, the tire degradation modeling was actually I would say, maybe not really an AI use case. What they wanted to do was to be able to capture the data. I mean, you cannot see it very well in this plot, but the idea is that they wanted to take all the data collected about the lap times and just do a polynomial fit to it. Of course, this is a polynomial fit that you have to do online with the information. As you get the information, you update the fit. But it's just a simple polynomial fit to be able to extract a little bit of information, right? And that was enough for them to get some value. But we also have a lap time prediction problem. We have this, information that is essentially a time series, and we are trying to predict how the time series is going to look in the future. That problem we tackle through some neural network-based models. So that require a different type of technology. You might tackle it with something perhaps simpler, maybe an autoregressive model, right? And we certainly tried different types of solutions. And then finally, we have the yellow flag prediction that we formulated as an anomaly detection, right? So accidents are, in a way, you can think of them as anomalies during the race. So can we use a classification model, right, to try to predict when if the next lap is going to be yellow or green? That was the way we approached the problem. But you might as well consider something more sophisticated, and turns out that there are actually tools that people have built to do classification for time series data. So you have plenty of options, and in choosing those models, you might also need to consider, how long is it going to take to make a prediction? That's another important factor, in particular for this type of problem, because in this problem we're trying to get a solution in less than a second, right? So I might have a very, very good model that takes 5 seconds to give me a solution, and even if the solution is very accurate, it wouldn't be useful because it takes too long to make the prediction. So that might also influence the choice of a model. After working on that iteration of the data, getting the data infrastructure, building prototypes for the models, then we went into deployment. Okay, now we wanted to make the first version of the models available for them to make decisions. And at this deployment stage, you are still working with the data scientists, you are still working with software engineers, but there is you might start interacting with other people in the organization. Now you need to integrate this into the operations of the organization. You might need to talk to IT. You might need to figure out if, do they already have a platform that they want to use to display this data, or do they want to create a new platform, right? And all of those are considerations into deployment. The other important consideration is also the infrastructure. What infrastructure are you going to use to run these calculations, right? So let me tell you first about, from an architecture, software architecture point of view, how the solution was designed. So this is a live streaming problem, right? So we want to do inference based on the inputs that we are getting from the race. So we designed a high performance event queue. So this is essentially the equivalent of that streaming event module that I showed you in the other diagram, right? So we use a tool that is able to handle data in a streaming mode. So this tool will receive the live streaming data, right? And then it will. You can think of it as time stamping it, right? So you know what data you have received, and it's event driven. So each package of data is an event, and then the model, for example, for yellow flag prediction, actually was 5 different models that were making predictions for what's the probability of having a yellow flag in the ongoing lab, in the next lab, and then 2 labs ahead, 3 labs ahead, 4 labs ahead. That's the way we formulated the problem. That model requires some feature processing. So we receive the live streaming data. Then the moment we receive the live streaming data, the feature processing takes that data, generate features, and return those features back to the queue. And then the model then take the features and make the calculation of the inference. So as a matter of fact, there should be another arrow here. And then the model generates the results. Those results get back to the event queue, and then they are taken by the dashboard that displays the results. So that's really how the architecture works. And all of this is essentially what happens live during the race. You have a version of your model making predictions, but you also need to care about the model training, right? So the model training happens prior to the race, and that's something that it doesn't happen online, but happens actually in the cloud. So you actually need infrastructure that can work in the cloud for model training and then work on-prem for model inference. And then just to give you an idea of what was the setup, where the calculations were going, this is an example of a track, right? So the cars are going through the track. The cars are generating that information every time they pass the collection point. All of that information of the car is actually collected at a control tower, and then that control tower sends the information to each of the teams. And the calculation of our models was actually happening inside a truck, sitting in a different part of the track, right? With a computer, on-prem computer in the truck. So we needed the latency of all of the process from data collection to inference to be less than 500 milliseconds. We were able to bring that to 200 milliseconds, right? But this illustrates, depending on the use case, how you have to think about your infrastructure. And it also illustrates how unique flexibility, in this case, to be able to have the application working both locally and on the cloud. And of course, the local version of it is the version that is providing the inputs for the data strategies. This is just an example of the type of output that you would expect out of a prediction. So the ideal outcome of the yellow flag prediction is that these 5 points in blue here are the predictions for the future. So at lab 16, we are predicting probabilities for lab 16 and the 4 labs ahead. And ideally, right, if you are actually able to anticipate the yellow flag that happens at lab 19, you should be able to see at least that the probability rises at lab 18, right? This is the ideal case. Unfortunately, not always we were able to make these predictions. These predictions turn to be actually quite challenging. And a reason for that is that if you look into the classes of accidents, there are different types of accidents. Some accidents are caused by a 2-car collision. Some accidents are caused by an engine failure. So the point is that with the data that we had, we were able to predict certain types of accidents better than others, which makes total sense. It's very hard, for example, to get anticipate an engine failure, right? Unless you have data coming directly from the car, from the insides of the car, which is not the case. But you might be able to predict certain types of two-car accidents just because you do have information to know, oh, these two cars are getting too close to each other, for example, and that might help you make the prediction. So that was one of the lessons, right? Like, in retrospect, I think that you need to look very closely to your data. Do you have enough signal in your data to make predictions? All right, so that was about deployment. Then I want, an important part of this is also sustainment, right? As you know, when you develop applications, software applications, those software applications need to be maintained, right? And that is a piece of the process that is typically neglected, but it's very important. Turns out that is even more important for AI solutions, because many of these models, machine learning models, are almost like living things, right? The data is changing, you need to retrain the models with new data. You might want to replace the model just because a new, better model came out, right? So there is a cycle of how do you maintain those and update those machine learning models. So just to illustrate this point, right, some of the aspects that you need to take into consideration is, for example, data monitoring. Data will be changing, right, the nature of the data. In this case, for example, I might have data from 10 years of previous races. It might be the case that for a specific track, right? Let's say, a specific track in a city. What about if they replace the pavement in the track? Well, now probably the data is going to be very different, right? So the model that I built with the previous data might actually be not applied the next year because the track has significantly changed. So that's something to keep track of. Continuous learning and model evolution. Models are changing all the time. So I might want to retrain the data. After the new season, I collect new data. I want to retrain my data with the most recent data, retrain my model with the most recent data. There might be new models that come out, or architectures that come out. So I might want to try something new, right? That's part of that sustainment cycle. You need also to develop infrastructure to be able to monitor these models and tell when they need to be replaced. And just to give you an idea of what could be next in this evolution, right? We talked this morning about how agents, for example, now are going a little bit farther into the process of decision making, right? Because agents in principle now are able to make the decisions, right? So in this version, we were developing models to generate knowledge for the human to make the decision. But you might as well imagine now these models feeding information into some reinforcement learning agent that would make recommendations of what decision should be made, right? And that could be the next stage for this type of solution, right? And another example of how you might in a second version of the solution think about a new technology to be incorporated. And I don't know why this turned out to be this, but the original slide actually displayed different industries and different images for each industry. I think this is the image for manufacturing, I believe. But the point is that, remember, I asked you to maybe think about how this would apply to your industry. So maybe at this point you're thinking, maybe there's a place for real-time decision-making in manufacturing, real-time decision-making in finance, and you might also start getting a sense of what will be required, right, to build these AI models in your particular industry. I think cases like these can be translated to many other cases. We saw a lot of examples, for example, of vehicles, sensor vehicles this morning, right? There are other industries where people are just increasing the number of sensors. The defense sector is one of them. In the public sector, there's also a lot of information that people could get from sensors and build systems that help with the decision making in those cases. Similar in finance, similar in other industries, logistics. So there is definitely plenty of opportunities for AI for real-time decision making. So I think I will skip this slide. If you want to know more about AQI, we can chat in the coffee break. And with that, thank you for your attention.